This video will be on section 2.5, the power rule. So the main topics in this section, we will look at the power rule for derivatives, and then we have various word problems, but we'll look at a couple problems that involve using the power rule or the derivative to solve them. All right, so the power rule for derivatives, pretty much going forward here through chapter 3, we're going to build up a whole bunch of rules for derivatives. That way we don't have to use that long, messy formula from before, the difference quotient. And the power rule is the first one to use that we learn. So the power rule for derivatives says this. It says let f of x equals x to the n power, where n is any real number. All right, so what it's saying here, our function needs to be just x raised to any power. It could be positive, it can be negative, it can be a fraction, it can be a decimal, any real number. Then the derivative f prime of x equals n times x to the n minus 1 power. All right, so that's the formula for x to the n is n times x to the n minus 1 power. And often what we'll do, especially when we do some problems later on in chapter 3, is we will write it like this. It's more helpful. So this says d over dx means do the derivative. That's the derivative of what's inside x to the n power equals n times x to the n minus 1. Right, so the prime, as we saw last section, the prime or the d over dx, those are the two main ways that we do the derivative. One thing I like to really mention about a lot of the derivative rules is similar to a lot of the log rules, is that if you memorize the formula, it's a lot harder than memorizing kind of what the formula says in words. So the way I like to think about it is if you move that n down to the front and then subtract 1 from the power, that's exactly what the derivative rule or derivative power rule says. So you bring the power down, then the new power is gotten by subtracting 1 from the old power. All right, so what we'll do is we'll just look at a few examples using this rule. But it is as direct as it sounds. Just you got to really practice this because it's easy to forget do I add 1, do I subtract 1, do I bring it down before, do I bring it down after? So let's just go ahead and see how it works. All right, the first one here, we want to do the derivative. So dy over dx means do the derivative. And we want to do the derivative of the function y equals x to the 18th. So as we only have one rule at this point, it's, we're going to use the power rule, but you really want to know why we're using the power rule here. It's because it's x raised to a power. So even though this is the only rule we have so far, it's good to start by noticing what rule we should use. And we want to do the power rule since it is x to a power. And if it takes on any other form, then we'll have different rules for that. All right, so the derivative, just kind of think about the formula, but in words instead of the actual formula. We bring the power down, so we bring the 18 down. We rewrite our x, and the new power of x is gotten by subtracting 1 from the old power, which, since it's a whole number, you can just do that in your head, but I'm going to leave it as 18 minus 1 for a second. Right, so you can see that's exactly using our rule here. If we had n equals 18, the derivative of x to the 18 equals 18 times x to the 18 minus 1. And the reason you'll want to do this is sometimes when you have fractions or negative numbers, it's a lot easier than you might think to do it too fast and mess up. But after you implement the power rule like this, it will simplify the power is all you need to do to finish it up. And here, 18 minus 1 is 17. So the derivative is 18x to the 17th power. Right, and we just got a few that are very straightforward applications like this, nothing else going on. Right, so number 2, we got to do the derivative of x to the negative 8 power. And you'll see why I like writing the formula down here and then simplifying instead of doing it at once. But once again, this is just x to a power. There's nothing else. So we must use the power rule. There will never be another rule for it. And the derivative of this, we get dy over dx. We bring the power down with the negative. We rewrite our x, and then we subtract 1 from the power. Right? And then once again, just simplify the power. There's nothing else to simplify here. The negative 8, there's nothing to do with the negative up front and the negative in the power because they're in different spots. So the negative 8 and the x stay alone. Negative 8 minus 1 is negative 9. So just be careful on that when you subtract 1 with a negative number, because especially if you don't do it a lot, which you might not have done a lot prior to now, it's easy to look too quickly and just put negative 7. Okay, so just be careful on that. Right. Number 3 here, just a different notation to bring in both. We have f prime of x, do the derivative of the function f of x equals x to the 9/2. And once again, it's just x to a power, so the only thing you have is the power rule. You'll never have anything else. Let's go ahead and work this out. F prime of x, I'm going to write it like this just because it really kind of wants it written like that. We bring the power down. Since it's a fraction, there'll be a fraction in front. We rewrite our x, and then we get our power minus 1. Right. And doing the power rule with fractions is very common. And there's anytime you're subtracting 1 off a fraction, it's pretty straightforward process. You might even get good enough to it where you don't have to do even this first step. But if we want to simplify as 1 power, as one number, 9 over 2 minus 1, we multiply the 1 by 2 over 2, get a common denominator. And then simplify. We got our 9 over 2 in front. Then the back thing, we multiply. We got 1 times 2 is 2 over 2. Remember, if it helps, you can write the 1 as 1 over 1. Whenever we multiply fractions, we multiply the tops together and bottoms together. And then we can combine them into one fraction now because we have a common denominator. 9 minus 2 is 7 over our common denominator of 2. All right, but once you do that, like I said, you might even be able, once you practice enough, to kind of skip this step and just realize what it's going to be. Plug it in, and then that is our derivative. Right. So kind of the shortcut after you do it a while is you'll remember, well, I'm getting a common denominator every time. So since I have a 1 here, it's always going to be subtracting off the denominator. So 9 minus 2 was the 7. Once again, you want to practice enough to where you just kind of see that. Don't necessarily just use it yet, because with the last example I have here, when you have a negative fraction, Same deal as up here. It can be, if you look at it too quickly, you might mess up the -1 part. All right, but once again, we're going to do the power rule because it's x raised to a power. And even though I wrote x for all of these, it's definitely true that you could have any letter here. So just whatever your variable is. All right, so exactly like before, I'm just going to write down the formula without simplifying anything. We bring the -4/7 power out front, x, and then we subtract 1 from the power. So I'm just going to write what that looks like. And if you're thinking about the shortcut already that I mentioned, this would be, this will become 7/7, but I'll write it on the side like before. But -4/7 minus 1. To get a common denominator, we multiply the 1 by 7/7. Then we get -4/7 minus 1 times 7 is 7/7. And finally, -4 minus 7 is -11/7. And once we plug that in, we have our answer. -4/7x to the -11/7. Right, but once again, I'm just reusing all the different notations. So this one has y prime to indicate derivative. So it can be y, it can be f of x, or whatever the function name is. It can be the d over dx, dy over dx. But that's really how we do the power rule without anything else being involved. Right? And you can already kind of see the shortcut that I mentioned happening. Since the denominator here was 7, this will have a 7 on top. -4 minus 7 is that -11, exactly what we got. All right, now of course not all functions are going to be just powers of x. When we did the derivative in the last section, through the whole process, what we did was we had numbers and we had additions and subtractions. We didn't have just x and x to a power. All right, so there's a few properties that are very useful to point out. The first two here come from the power rule. And the first one says the derivative of a number times x is just the number. Now, if you remember, the derivative is pretty much like the slope of a line, the average rate of change. And this is a line with slope c. So there's a lot of ways that you can actually figure this out, and that's one of them. The other way is if you use the power rule. You can just memorize this, but I'm going to show you why it's true. From the power rule, the derivative of c times x. Well, what I'll do is actually do just the derivative of x. And because there's not a power written there, I'm going to write x to the 1 power, because that's the same thing. And then when we do the power rule, we bring the 1 down, we rewrite our x, and we subtract 1 from the power. And here we can see that 1 minus 1, the power on x is 0. Actually, let me leave that in orange. And anything to the 0 power is 1. Right, so the derivative of just x is 1, and then the c stays along for the ride. Right, but once again, just remember when you have a number times x, the derivative of that is 0, or sorry, the number. Now the next one says the derivative of just a number, notice there's no x here, it's just a number, is 0. Okay. And this one, I'll just explain it in the terms of the lines again. The graph of just a number is a horizontal line, and a horizontal line has slope 0. You can also do it with the power rule. You would start by, in place of k, you would think about it as k times 1, and then write the 1 as x to the 0 power. So when you bring the 0 down, it's multiplication of 0. But that's a little more complicated. But once again, remember these rules. And like I said, it's really helpful to remember them in words. They both come from the power rule, but they're both also so common that it's useful to actually point them out separately. So once again, the derivative of a number times x is just the number, and a derivative of just a number is 0. Okay, you'll notice I didn't have any of those up here because it's not as obvious how to deal with them. Right, now the next two properties will allow us to actually deal with the numbers here, like the c. And then also, what if we're adding or subtracting something? So it says let a and b be constants and f of x and g of x be differentiable functions. Then we have the following two rules, which once again, memorizing in words, and once you practice them enough, it'll become more straightforward. The first one says if you do the derivative of a number times a function, you can bring the number out. Right. So if you have, like I said up here, with the c times x, what I really did here was I could bring the c outside. So I would get c times the derivative of just x, which is 1. And that's why the final answer was c, because it came from c times 1. We'll see how to use this and the next one in the next steps, the next few problems to practice. Right. The second one here says the derivative of a function plus another function. What it says here is do the derivative of the first part plus the derivative of the second part. Basically, do the derivative of each part not of, if the terms are added. And even though it's not really written here, I'm going to add it in. It's also the case if it's subtracted, because subtraction is just adding times a -1. One thing I want to really point out here, this is important. Derivative rules are kind of like log rules in that if you don't have a rule for it, you can't do it. So I'll make a really important note here. These rules say nothing about multiplying or dividing functions. Right? In fact, it won't be until section 3.3 where we learn how to do the derivatives if there's multiplication or division. Right? But what we'll do, kind of combining all 4 of our new rules here, along with the power rule, is we'll do a few derivatives that look a little more complicated, but once you do it a few times, you really start to notice the pattern, and you don't really even think about using these rules so much. You just kind of do it. Right, so the first one says, find the derivative of h of t if h of t equals -8t cubed minus 7t plus 2. Right, so the first thing to do, you don't look at the power rule. What we do is if you have more than one term, and we have 3 here, we want to do the derivative of each part. That's the first thing to look at. Right? And you can do it in line, or you can do it on the side. Like you can do negative 8t cubed and negative 7t and 2 separately. What I like to do is I like to do them in line, but I like to indicate doing the derivative of each part. So here our variable is t. What it's going to look like, the derivative of our function. Oops, I need to close that off. But what this says is do the derivative of our function. This is how you can really properly organize your work. Right, it's just really rewriting what we're told to do. And then we want to do the derivative of each part, meaning I can split it up like this. All right, so I take each part, the negative 8t cubed. Oops, shouldn't have a double minus here. I put the minus out front so that we have the derivative of negative 8t cubed minus the derivative of 7t plus the derivative of 2. So this says do the derivative of each part. That's using the last rule here. And once again, especially when you start learning this, at least my experience was that it's almost harder to watch it the first couple of times than do it yourself, because once you see how it works out, it comes a lot quicker. But once again, that's my experience. All right, so it says do the derivative of each part. Now for the first one here, we don't have just t raised to a power, we have that negative 8 there. So in order to use the power rule here, we need to take the negative 8 out. Right, but that's exactly what this rule says up here. If we have a number, negative 8 times a function, which happens to be t cubed here, we can bring the number out. So we get negative 8 times the derivative of t cubed. Now the next one here, I'm going to just bring down the minus. And then this one says do the derivative of 7 times t. But that's also this rule up here. It says the derivative of a number times x, but now our variable is t, which is the same. The derivative of a number times t is just that number. So this is that rule. Right, so when you do the derivative, you get rid of the derivative symbol and we replace it with what the derivative is, which is 7. Right, the derivative of 7t is 7. All right, once again, I just brought the minus sign down. That's why the minus is there. For the last one, I'm going to bring the plus down, and then this says do the derivative of 2, which is just a number. And this is one of the best rules because there is no ambiguity. You don't have to worry about letters. The derivative of a number is always 0. So you just plug in 0 there. Right, and now we're almost done. We can simplify this because we don't need the minus or plus 0 anymore. When you know you're done when you've done all the derivatives. So after we do this derivative of t cubed and simplify it, we will be done. All right, so I know we started with 1 and then it seems like we kind of made it longer, breaking it down into 3, but that's the proper way to do it. Once we do all derivatives, We are done. And this one is finally in the set up in the way where we can just use the power rule because it's just the letter variable t raised to a power. Once again, it's very important that you remember what these rules say. That's why when we did the power rules up here, I mentioned it's just x to a power. There wasn't a number out front. There wasn't anything added or subtracted on. It was just x to a power. Right. All right, so when we do the power rule now to finish up, we got our -8 out front. The derivative of t cubed, the power rule says bring the 3 down. Rewrite our variable t, and then subtract 1 from the power. 3 minus 1 is 2, so I'm just going to write it like that. And then the remainder, the -7, we don't need to write the +0, just for the same reason we never do. It doesn't do anything to our answer. And then our final answer, multiply these. -8 times 3 is -24, t squared, and then -7. Right? And that is the derivative. Now, like I said, once you practice these, it really does take a lot of practice. That's why there's quite a few homework problems, but you'll start to see the pattern. One thing that I can kind of point out now that -24 is because I know I'm going to bring that 3 down. So -8 times 3 would become the 24. The reason the power becomes 2 is because we subtract 1. Reason we have -7 is I know the derivative of this is just -7. And the number when I do the derivative just goes away. But you really want to take your time, practice these. If you don't get the power rule down with the other rules that we have in this section, it makes doing stuff in chapter 3 almost impossible. And really the rest of the class, you've got to get it down. Right? So the second one is just very similar, but more practice with fractions and negative numbers of our power rule. At this point, we can't really make it any harder because you look back at the last problem, it used all of our rules. We used the power rule, we broke it apart using this rule here. We took out numbers using this rule here. We used that a derivative of a number times x is just a number. And we used a derivative of just a number is 0. Right, so this is really for now as bad as it can get. All right, so this one says find the derivative of 5x to the -2 plus 3x to the 1/4. This one's already set up in the way I wrote it the first time, so we want to start by doing the derivative of each part. All right, so I'm going to do exactly what I did, split it up over the plus. Right, now, based on what we saw last time, we don't have any of the special rules here because these both have powers on them that aren't 1 or 0. And what did we do last time? Well, look back here to the -8t cubed. Right, what did we do? In order to use the power rule, we had to take that -8 out. So now we're going to do the same thing here. We're going to take that 5 out of here and 3 out of the back one. So we take the coefficients out, the numbers. So we can use the power rule. All right, so let's just do that. Take the 5 out, and then we do have the derivative of what's left inside, x to the -2 plus 3 times the derivative of x to the 1/4. And now on each one of these, we can use the power rule because they're both x raised to a power. no numbers in front to deal with, no additions or subtractions. All right, and you'll notice a pattern here. Pretty much whenever you have to use the power rule, it's really going to be almost the last rule you're going to use in a problem. All right, so the first one here, we bring the -2 down, we get x, and then I'll just write out the intermediate step. We subtract 1 from the power, plus 3. Then we bring, in the second one here, we bring the power down 1/4, we get x, and then we subtract 1 from the power. All right, let me just box them in so you can super make sure where they came from. All right, but once we're here, we know the last thing to do. We need to simplify the power. Also, because we have multiplication here with the coefficients, let's just make sure we multiply those two, make it a little bit simpler to read. And so here, 5 times -2 is -10, x. -2 minus 1 is -3, plus 3 times 1/4 is 3/4, x. And then 1/4 minus 1 is -3/4. Right, you can find a common denominator or sort of use that shortcut that I showed you before. We're going to do 1 minus 4 on the top, which is -3, over the common denominator, that it will become 4. But once again, that's really practicing using these rules. These rules are very important, and once you do them enough, it really does become second nature when you do derivatives. You just kind of break it down. Oh, I'm just going to do the derivative of each part. Okay, well, now I can just look at this. I know I'm going to bring the -2 down and subtract 1 from the power. And you can get this -10x to -3 pretty quickly. Same deal for the second part. All right, but once again, you'll notice that we didn't have any multiplications or divisions here for a reason. We don't know how to do those derivatives yet. All right, so the last one that's really to make sure you're using your not only your derivative rules properly, but you might have to reformat some problems in a different way. All right, so this last one, we want to do the derivative of the function 3x to the 1/2 divided by 4 minus 7/2x cubed. All right, so once again, we have multiple parts here. I'm going to do the derivative of each part. You'll notice that's always my first go-to. It doesn't matter that we have fractions here. We'll be able to do this problem. Right. So our variable is x. We got d over dx. 3x to the 1/2 over 4 minus the derivative of 7/2x cubed. All right, now the next thing, there's actually a couple things we're going to need to do, but if you follow kind of what we did last time, what did we do after we said do the derivative of each part? We brought out the numbers. So bring out the coefficients. And if you have a fraction, it'll just come out as a fraction. So the first one, when I write it, I'll have a 3/4 out front, and the second one, I'll have a 7/2 out front. All right, so when I bring out the 3/4 from the first one, what's left inside, we only have x to the 1/2. And the fraction's gone because we brought the entire 4 out from the bottom. Then we have minus. The second one, we bring out the 7 on the top and the 2 on the bottom, times the derivative. My apologies. I'm going to rewrite it below so I have enough room. So We got 3 over 4 times the derivative of x to the 1/2 in the front minus the 7 over 2 times the derivative. Now, when you bring out the entire numerator like we did here, it doesn't go away because we still have an invisible 1 on top. The reason why we can get rid of the denominator is it's like dividing by 1 does nothing, but having a 1 on the top is important to not get rid of. And then on the bottom, we're left with x cubed. All right, now there is one thing that's different about this problem from the rest that you have to be careful on. So this first thing we could use the power rule on. It's just x to a power. The second one is not quite perfect for us. We have x to a power, but it's in the denominator. So before, it needs to be in the numerator. What we need to do is bring the x cubed up to the top of the fraction. If we do that, then it will look exactly like this because the 1 goes to the bottom and then dividing by 1 doesn't change anything. So we need to bring it to the top of the fraction. And in order to do that, you're allowed to do that is you need to change the sign on the exponent. Right, so you're allowed to bring things from the top to the bottom. You just have to make the proper adjustment. All right, so for the first one, I'm not going to do the derivative yet, even though we could, because I want to do them both at once. And then for this one here, we bring the x cubed to the top. The exponent becomes negative, so we get -3. Right, keep in mind that it's changing sign, so if it was already a negative exponent, when we bring it to the top, it would become positive. Right, but now we can do the power rule of each. Each one is now x to a power. All right, now you don't need to wait to do both to actually do them both. Like I said, I could have done this one first and then, done the second one after. But if possible, I prefer to do all the derivatives in one step. All right, so we can do the power rule now. The derivative of x to the 1/2, we bring the 1/2 down, we get x, and then we subtract 1. So we got -7 over 2 times, bring the power of -3 down, we got times -3. And then we got x to the -3 minus 1 power. Now simplify exactly like we have been. We're going to simplify each exponent and also simplify the coefficients. So the first thing we have 3 times 1, which is 3 over 4 times 2, which is 8, x. And if you find a common denominator, 1/2 minus 1 is actually -1/2. And kind of spell it out the way I mentioned the other ones. You would do 1 minus 2, which is -1, over the common denominator of 2. And then the second one here, we got -7 times -3 is positive 21 over 2 times 1, which really isn't in there, over 2, x. And then -3 minus 1 is -4. And that is the derivative of this. One thing I guess I didn't mention in the previous one, even though exponents were negative, you have no obligation to rearrange them and make them positive. This is simplified and good. One thing you will see as we work through and have more and more derivative rules is that the final answer will almost look like it's factored in a lot of problems, and people want to unfactor them. But once you do the derivative, just leave it alone. This is fine. We don't need to simplify anymore. And once again, we know we're done because we've done all the derivatives and all the powers and all the numbers are simplified. All right, so like I said, we'll finish up this section looking at a word problem using the power rule. You can see where the derivative comes into play, and also, interpreting your answer. Right. So I'll just kind of like preview the problem. It says the total sales of a company in millions of dollars t months from now are given by S of t equals 0.03 t cubed plus 0.3 t squared plus 4t plus 8. So the first part says find s prime of t, so find the derivative. The second part says find s of 0 and s prime of 0. So this s prime, or sorry, 4, not 0. Not sure where the 0 came from. But this is something that we actually dealt with last section. We'll just have a good reminder. And then the last part, it actually tells you to interpret these two results. What do they mean in words? And the question will be multiple choice as far as, which one is correct, but you want to understand what each one is telling you. Right. All right, so the first thing we got to do is find the derivative. And in order to find the derivative, we've got to do the derivative of each part. Now, after this section, I'll probably stop writing it on every problem, but we need to do the derivative of each part. Okay, so we got the derivative. You'll notice I've always matched the letter down here, t, with the letter in the problem, because it says do the derivative with respect to that letter. 0.03 t cubed plus the derivative of 0.3 t squared plus the derivative of 4t plus the derivative of 8. Now in each one of these, we don't have to manipulate it with like last time with a fraction. All we have to do is bring the numbers out of the first two. So you'll see once again, I'm taking the same steps every time. And there's a reason for that. You just want to be very procedural with this. So we bring the 0.03 out of the first one, and we're left with doing the derivative t cubed on the inside, plus, and then bring the 0.3 out of the second one, and then we have the derivative of t squared left. Now you hopefully remember why I'm not bringing the 4 and the 8 out of this one. It's because these are a couple of our special rules. The derivative of a number times the letter is just the number. And then the last one, bring down the plus, the derivative of a number is just 0. I'm just writing derivative rule here to remind you, but we did that. We used that in this problem before, and just a reminder, we're using these rules for those of you that might pause and go back to the videos. Derivative of a number times the letters, just the number, and the derivative of just the number is 0. Right? Now that we're here, we brought the coefficients out, which means we can do the power rule on each. Right, we've already done the derivatives on the back ones, which means they're just going to stay as they are. We got 0.03, the derivative of t cubed. We bring the 3 down, rewrite our t, subtract 1 from the power. 3 minus 1 is 2, plus 0.3, then times the derivative of t squared. We bring the 2 down, so we get a 2t, and then subtract 1 from the power, so the power is 1. And then we need to make sure we bring the 4 down, but plus 0 doesn't do anything, so we can leave that off. And now that you've seen a couple of those, you can kind of just remember, oh, the derivative of just a number is 0. So you might even be able to just not even write that 0 there. Just leave it gone. Right, but now we simplify. 0.03 times 3 is 0.09. That looks kind of funny. Let me rewrite that. And then we got a t squared plus 0.3 times 2 is 0.6. We have t to the first power, which is just t, so I'm not going to rewrite the power, and then plus 4. All right, so that is s prime of t. All right, now the second one, it says find s of 4 and s prime of 4 to 2 decimal places. All right, so s of 4, this is telling you plug in t equals 4 to the original. All right, we don't have a prime there. So we have 0.03. Make sure you're using the original. In place of t, we got 4, so 4 cubed, plus 0.3 times 4 squared, plus 4 times 4, plus 8. All right, make sure you're using the whole original, not anything to do with the derivative at all. And then we'll plug it into our calculator. So we got 0.03 times 4 raised to the third power, plus 0.3 times 4 raised to the second power, plus 4 times 4, which is 16, plus 8. And we get 30.72. Right, so that's a problem that you could have done pretty much at the very beginning of college algebra and maybe even before that. And then the second part, we want s prime of 4. For s prime of 4, you don't use anything here about s of 4. That's not important. You used the formula for s prime of t and then plug in 4 there. All right, so we want to plug in t equals 4 into s prime of t formula. We got 0.09 times 4 squared plus 0.6 times 4 plus 4. And plug that in our calculator. We get 7.84. All right, now something that I always like to mention is that the numbers of these two answers don't have really any involvement. Meaning this could be a million, this could be 0, and they could be reversed. They don't interact with each other. They tell you different things. So you don't really want to try to find a pattern, like how does this compare to this? Because there is no pattern. All right, so the last one is to interpret these results. They give you some results, so they're not asking you to interpret what you got up here. What does s of 12 equal 151.04 mean? Well, you have to go back and read the problem again. So what s of t means is it's the total sales of a company in millions of dollars t months from now. All right, so the t is the number of months. This is telling you in 12 months, the total sales of this company in millions, because we're told it's in millions, will be 151.04. That's the regular function. That's what the regular function means. We can just read it off like that. Now, what does s prime of 12 mean? Right, if you know what s prime of 12 means, we can just fill in the number. So remember, the derivative is the rate of change. Since we're talking about sales here, it's going to be how the sales are changing. Right, so s prime of 12 equals 24.16. We can still say in 12 months, the rate of change of total sales We can still say the in millions. So it almost looks the same, except we replace sales with rate of change of total sales. And the other thing you want to make sure you do is, since this number is positive, we want to say it's increasing. Will be increasing by 24.16. If it was negative, if we had a negative number here, it would be decreasing. For a problem with dealing with sales, your sales shouldn't go down because it's the total sales, it can only go up. But that's the interpretation. So I'll just write that as a little note here. If the derivative is negative, we say it is decreasing. Since it's positive, for this one, we have increasing. Right, but that's really it for the power rule for now. Like I said, there's a lot, quite a few homework problems just for you to get through the routine of this. And I really can't recommend enough just, really practicing this section. The next section that I do, 2.7, we'll add in some business words, but ultimately it's going to be more power rule practice. Right, and that is that.